In this video, I want to introduce you to a very important concept in chemistry that we will be using from now until the end of the year, and that is the mole. I want to start by thinking about three ways that we measure matter. Sometimes we count individual items because we want to know exactly how many individual pieces we have. Other times we take the mass of an item because we want to know how much it weighs. Or with some things, we measure the volume. We want to know how much space it takes up. When we're thinking about measuring atoms, there are times where we want to count the number of atoms, and there are other times when we're measuring those atoms by mass or by volume. Another important concept in understanding the mole is this idea that we use names to mean certain numbers. We use the word dozen when we're talking about 12 of something, or pair when we just mean 2. You might know that a gross is 144 of something, and in your measurements, you probably learned that 1 yard is 3 feet, or you can think of it as 36 inches, and 1 meter is 1,000 millimeters. To switch from one unit, one of the words for the way we're measuring the numbers, such as meter or millimeter, you use unit conversion. Now in the metric system, we can just use a decimal point, but if you're talking about something like eggs and dozens as compared to individual eggs, or comparing inches to yards, you need to use a process known as unit conversion. Sometimes you also see this described as dimensional analysis or sometimes factor label analysis. And basically you do something like this. You say, oh, I have 42 eggs. Well, how many dozen is that? Well, with my 42 eggs, I'm going to multiply it by what I know the relationship is between dozens and eggs, and that is that 1 dozen is the same as 12 eggs. So I'm going to make a fraction where dozen is on the top and eggs is on the bottom. That's so you can cancel out the eggs. You can get rid of that unit, leaving the answer in dozens, and when you do the math, you get 3.5, and then dozens is the unit that is left. That's unit conversion. You're converting from eggs on one side to dozens on the other by using a fraction in the middle that is really talking about the same thing in the numerator and the denominator. 1 dozen is the same thing as 12 eggs. We just have different units. So atoms are much too small to measure individually. We really can't count them out. And so scientists work with packages of atoms, a group of atoms or a group of particles if we're talking about molecules, because there's more than one atom making up a molecule. The unit for measuring particles of matter then is the mole, which actually comes from the German word for molecule, has nothing to do with the little creature that lives underground. 1 mole of any kind of particle is 6.022 times 10 to the 23rd particles. Now this, of course, is 10 with 23 zeros after it, or a 1 with 23 zeros after it, so it is a very big number because atoms are very small things. It also has 4 significant digits, so if it has 23, we're going to actually be going 22 places. It's like our decimal point is going to move this way 22 places. There's going to be a whole lot of unknown, uncertain digits in that number. We really are only certain about these first 4. They're the only significant digits. So it is a measurement that does include a little bit of estimation. But in general, 1 mole, 6.022 times 10 to the 23rd particles. Atomic mass is really a relative measurement. We're picking the size of an atomic mass based on something that already exists instead of having it being a true measurement that's independent of reality. Because 1 mole is the number of atoms in 12 grams of carbon-12, and of course the atomic mass of carbon-12 is 12 atomic mass units. So the mass of 1 mole of any element is the atomic mass in grams as the unit. Because we see here our atomic mass of 12 atomic mass units is the same as 12 grams. The number is the same, but the unit has changed. And this is another place where the periodic table becomes very helpful. The mass of one element, you can look it up and see what is given as the mass amount on the periodic table and use that directly, Or if you have a compound, you will add the atomic mass of all the elements in the compound and then take that number in grams to give you what is known as a formula mass, or sometimes it's called a molar mass. So here are some examples of 1 mole of different substances, how much that would mass. And inside each of these piles, you know you have 6.022 times 10 to the 23rd individual atoms. So zinc would mass, 1 mole would mass at 65.4 grams, while magnesium is 24.3 grams, copper is 63.5, and so on. Our larger elements, of course, are going to have heavier masses than the smaller elements because every additional proton and neutron is going to add 1 more mass unit. Here are some compounds, and those measurements for 1 mole are even larger because you have to count all of the ingredients in the compound. So copper sulfate, this is something that we've worked with quite a bit in class, and its formula is CuSO4. This copper 2 sulfate. And so you have 1 copper atom, 1 sulfur atom, and 4 oxygen atoms. So there are 6 atoms for every 1 molecule, and there is 1 mole of molecules present, which is why we have 249.7 grams equaling 1 mole of copper sulfate. We can also see moles in how we measure gases in volume because scientists have discovered by a number of experiments that 1 mole of any gas will have a volume of 22.4 liters if that gas is at STP. And STP is when it is 0 degrees Celsius and under 1 atmosphere of pressure, which is basically what we live in. The size of 22.4 liters is slightly larger than a basketball. You can kind of see the outline here of a box, and it's bigger than a basketball. But it doesn't matter what's inside that box. It could be helium, which is going to have a mass of just 4 grams because it's a very small atom. Or it could be nitrogen with a mass of 28 grams. Or it could be methane, which is CH4 with a mass of 16 grams. But the particles, the number of atoms, is exactly the same in each one of those amounts, in 1 mole of each of those gases. Basically because of how gases are very spread out, the particles are far apart from each other, and so they're occupying the same volume. So you use those relationships between number of particles and moles and mass and moles and volume in a variety of calculations in science class. And you're going to have plenty of time to practice this. So for example, you might have a question that asks how many particles are in 0.04 moles of magnesium. So you know 1 mole has 6.022 times 10 to the 23rd particles. So you're going to know that's 1 mole, but you don't have 1 mole. You only have 0.045. So you're going to multiply these two numbers together to see what the number of particles is in this less than even, it's a tiny, tiny piece, 45 thousandths of 1 mole. On your calculator, answer will probably look something like this. You'll have 2.7, and we would round this off to 7.1. It would be 709. And then you're going to have an E. It might be a small e, it might be a capital E. And that E, remember, is what your calculator is telling you it's times 10. And then the next spot after the E is going to be your exponent. So it's going to be a 22 in this case, or it'd be like 10 being raised to the 22nd power. So on your calculator, you're going to see something that looks like that. The E might be capital, it might be small, depends on your calculator. But that means that you are taking this decimal point 22 places to the right, or you're adding 20 zeros after that 1 in order to get to the number. You're still talking about a very large number of particles, even though we have a pretty small part of a mole. Or you might be asked, how many carbon atoms are there in 0.75 moles of MSG? And then you have the formula for MSG down here. It's a food additive that adds flavor. Here is the molecule. You see we have 1 sodium atom in that molecule, and there are 5 carbon atoms in that molecule, then 8 hydrogens, a nitrogen, and 4 oxygen. So in 1 mole of this molecule, there are actually 5 moles of individual carbons. We don't have 1 mole, we've got 0.750 moles, and we know each part of that it's going to be a proportion of those 5 carbons. And then again, we're being asked how many individual atoms, and so we're going to have to multiply that by 6.022 times 10 to the 23rd. Again, using your calculator. In order to get this times 10 part, you're either pushing an EE button or sometimes it's an EXP button. It kind of depends on the individual calculator. If you do all of this multiplication, you'll get an answer that's going to round off to, for 3 significant figures, it's going to round off to 2.26. And then you would have an E of some form, capital or small, and a 24. So again, this number actually represents 2.26 times 10 to the 24th power. That's how many individual carbon atoms you have in this 0.75 moles of MSG, a molecule. Or here's one using volume. A large helium tank typically contains 421.9 liters of compressed gas, which is enough to fill 50 party balloons. So how many moles of helium are in this tank? So if you remember, I said every single, a mole of any particular gas is going to be equal to 22.4 liters. So 1 mole is the same thing as 22.4 liters. Now, we don't have 22.4 liters, we have 421.9 liters. And so again, if you're setting this up to multiply these two together, we'll be able to cancel out our liters. Our answer would be in moles. And we were basically taking 421.9 and dividing it by 22.4 to give us an answer of 18.8 moles. You notice I'm having everything round off to 3 significant digits. That's typically what I require in my classes. Other teachers may require more or less significant digits. And finally, we have some molar mass or formula mass calculations. So what is the mass of 1 mole of sodium chloride? So we know sodium chloride has got 1 sodium and 1 chloride. And if you go to the periodic table and look up the atomic masses, on the periodic tables we use, it'll tell us that sodium is 22.990 as an atomic mass. And again, that's 5 significant digits. I don't think we need to work with so many, so we can round that down to 23.0. And atomic mass units are just translated into grams when you go from individual atoms to moles of atoms. So 1 mole of sodium is 23.0 grams. Chlorine, on the periodic table, we see that's 35.453. Again, turning that to 3 significant digits, we'll say it's 35.4 because this 5, remember the science rounding off with 5s is that it keeps an even number, so the 4 is not going to change. And then if we add these two together, because a sodium chloride will contain 1 of each, you see that 1 mole is going to be 58.4 grams. To get a little more complicated, what is the mass of 2.78 moles of water, of H2O? So we're going to have 2 hydrogens and 1 oxygen, in the water. Hydrogen by itself, again, the periodic table is 1.0079, so we're going to round that to 1.01 for atomic mass units, and we're going to have 2 of them, so that's going to turn into 2.02. And then oxygen is 15.999, so again, that's going to round for 3 significant digits to 16.0. And we just have 1 of them, so if we add our 16.0 to our 2.02, and again, we're going to make it 3 significant digits, so we'll knock off that 2. We have 18.0 as the mass of 1 mole. That's just 1 mole of water. We have 2.78, so we're going to multiply. Oops, that's not moles, that's grams. 18 grams in 1 mole. We're going to multiply it by our 2.78 moles. And this is really grams per mole, so of course the units would cancel for those of you that are precise about those things. And then 18.0 times 2.78 is going to give us a final answer of 50.0 grams of water found in the containing 2.78 moles of water. So to summarize, the mole that is used in science is a way that we get a handle on the number of atoms, the number of particles of either elements or molecules in a particular sample, or it helps us understand the mass that is necessary for a certain number of particles, or the volume that is necessary for a certain number of particles. So the mole is a very useful tool. It is going to become more and more important as we move more deeply into chemistry, and you'll be able to see how it helps us plan for chemical reactions to give us the products we want in the amounts we want.